Hello, my name is Brarawal, and welcome to my video for Lab 3, which is a magnetic field of a bar magnet. So in this lab, we're going to measure and observe the magnetic field created by a bar magnet and determine the distance dependence. The physics principles in this lab is the PHYS law and the magnitude of a metal bar, magnetic bar. Purpose. So we're going to explore the correlation between magnetic field and observable distance, further understand and draw conclusions from the PHYS law. Procedure. We're going to determine the direction of magnetic north. We're going to lie the phone flat on table, rotate until the x component is 0. Set up meter stick orthogonal to north. Find magnetometer of phone. Position phone perpendicular to meter stick with x and y direction. Mark axes with tape edges. Finally, move phone at various distances along meter stick, on axis and at a 45-degree angle. Record magnetic field components in spreadsheet. Materials used in this lab are the bar magnet itself, a ruler, pieces of tape, magnetometer app, and a smartphone. The assumptions we're making in this lab is the Earth's magnetic field's x component by orientation of the phone is 0. The value of n is expected to be around -3. The magnetometer chip is located on the top left of my smartphone. The data measurements. The collected data measurements for the magnitude of the magnetic field are summarized in this table. In order to find r, we'll need to generate a logarithmic plot of this data. By doing so, we're converting the equation of the magnitude of the bar magnet into this equation, which is presented in the form of y equals to mx plus b. N is the slope of the graph, while the y-intercept is the natural log of k. After forming the plot of the data, we can now use this graph to extract our values. The equation of our graph is y equals to negative 2.6395x minus 13.286. The slope is found to be negative 2.6395, which is close to the value of -3 we were aiming for. We can use the value of natural log of k, the intercept of the graph, which is negative 13.286, to calculate the magnitude of the magnetic dipole moment by combining and rearranging the two equations, as shown here, which we find to be 4.2 am squared. The off-axis magnetic field measurement. We position phone D-perp in x and y direction, measure magnetic field using magnetometer app with average D-perp of 0.20067 meters. The average magnetic dipole magnitude is 4.901 e to the -5 Tesla. So this is the code we use for the Glowscript IDE. This is the equation for the PHYS law. And we're using 6 observable locations, including 4 perpendicular ones and 2 on axis at a set distance from the center of the magnetic dipole. We can calculate B for each of these locations, the magnitude of the magnetic field due to the magnet. Finally, we can use the arrow function to display our model on the right. So here's our Glowscript model. As you can see, the on-axis vectors are in line with the dipole moment, while the perpendicular vectors are facing the opposite direction. Also, if you observe, you can see that the magnitude of the vectors perpendicular are half and the opposite directions of the ones on the axis. Reflection questions. So what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? All magnetometer readings would be skewed in the direction of north due to the positioning of the phone. Values of k, n, and mu would be less accurate. The second reflection question is, what if you were to stick 2 identical magnets together, end to end, and run the experiment again? How would you expect your measurements to differ? Direction of the magnetic field would be the same, and assuming a length of magnet is minimal, the magnitude of magnetic field would be approximately double. Thank you.